Who's gonna get shocked this class?
Hopefully, no one's going to get shocked this class. However, no guarantee on that one. Poor Kenneth. Well, actually, Kenneth had to say. I will claim it was Kenneth's fault, but I didn't say it was my fault. All right, so let's start out with a simple question. The electric charge is at the sort of heart of everything that we will do in this class. And so, what is electric charge? And the answer is? Have you heard of electric charge?
Yes.
All right, got a couple nods there. Okay, no one at least vehemently looks scared of it. All right, what do you know about it?
It can be positive, negative, or neutral.
Okay, so we got that. All right, so what we know. Let's see if that pulls it down. What we know. Positive, negative, or neutral. All right, what else? That's it. I know there's at least one other thing that people know.
Their type of forces.
I'm going to throw the word force on there. I would not agree with your statement, but you're correct adjacent. The correct adjacent, it creates forces. Charge is not a force itself, but it can exert a force.
Type of charge can affect movement. The type of charge can affect direction of movement
Okay, how?
by working with or against whatever the type of movement is.
Okay, all right, since we got into forces, what do you know about forces in charge? Are you gonna make me say that first word? Okay, you're not gonna make me, okay. Are you gonna fill in the awkward space more?
Nope.
Okay. Someone else wanna fill in that awkward space? All right, despite what she said, I'll go ahead. Opposites,
Attract.
there we go. Yes, opposites attract. Opposite charges. Attract. And like charges. All right. What else do we know? Or is it time to get back to what is the electric charge? Or in the context of this class, what is charge?
Is it like potential energy kind of?
Like, you have to be louder.
Kind of like a potential energy?
There is a potential energy associated with it. Let's do a trip down memory lane here. If there is a potential energy associated with electric charge, what can you tell me about the force?
It has,
Pardon?
it has force because it's creating force.
Okay, we can be more specific than that.
Yeah.
We can. What do we know about what's the formula for potential energy?
One
Oh, no. How about this half over here?
Wait.
Thank you, Stephanie. Say it again.
Which one?
Why is there more than one? When is there going to be a potential energy formula? apparently the chapter 7 had a huge impact on their lives.
Never mind, it just ignored me after that.
Did you say work? It is related to work, but you know, there's always that hope every semester that people will remember something that they did in 151, but apparently
It was ages
you're like
ago.
most classes. Pardon?
It was ages ago.
I know what it was.
It will come back to us.
For some of you, it wasn't as long ago as it was for Luis. If there's a potential energy formula, is the force conservative or non-conservative?
Wait,
Repeat it, if it's.
If there's a potential energy formula, is the force conservative or non-conservative?
conservative.
Like you mean it.
Conservative.
Yes, it is a conservative force involved here. The electric force is a conservative force, so when it is involved, if it is the only force involved, energy definitely is conserved. Thus, we need a potential energy formula, because as potential energy changes, kinetic energy will change. We will definitely get into that in more detail. I know, a little bit of a teaser, a little bit, keep you coming back just for the excitement of that. All right, so let's get back to what is electric charge and why it really wasn't a fair question. Here's the official answer. Yeah, I know. It was sort of disappointing. The electric charge is a property that we know there's 3 types. We know 2 of them, if I have 2 positives or 2 negatives, they will repel each other. If they are opposites, they will attract. If it's neutral, it might attract or it might not, depending upon the nature of the neutral object. So we really don't know fundamentally what it is, but we put this label on this property of materials. Because we can't go far without using symbols, because I don't feel like writing electric charge over and over again, let's talk about what is the symbol for it. And as you would guess, the symbol for electric charge is Q. Now, oftentimes, little q represents a single charge, big Q represents a collection of charges. There's some gray area in there. I will use one or the other. I'm not specific about, if I use capital Q, it should mean I have a collection of charges, but not necessarily. It could just be, that was my mood when I wrote the Q. I believe it's Q for quantity. There's this quantity of something. The units. The SI units. Pardon?
Volts?
No. That will come in later. We'll take another shot.
Watts?
That will come in later.
Ohms.
That will come in later. You are hitting a lot of the key units that we will be talking about this semester. Watts not as much as the others.
Which one did we say already?
You've done ohms, watts, and
Volts?
volts. Another unit that doesn't answer this question that we will be using also is joules. It is the Coulomb. Sorry, if someone was about to say that and I just spoiled it for you. Anyone want to take a wild guess for whom this unit was named? Hey, there you go. We will run into a unit at some point which is based upon a name, but is actually not the person's name. But we will get there. As well as the trivia of 2 great Scrabble words that usually textbooks leave out, but we will get there. All right, what is electricity? What was the last thing, Lauren?
I just add electricity electricity is the flow of a charge? No,
That would be current.
current.
You're looking at some definition from online?
Oh no, I'm just staring at the homepage of the class.
Ah,
and trying to inspire.
Staring lovingly into the picture.
Yeah.
Okay. All right. If some of you recall, when people mention what is gravity, what was my general response?
Oh,
Pardon?
What side?
Not necessarily what type, but you are close. Remember, gravity is this huge topic of which we studied a tiny little sliver of it. We talked about acceleration due to gravity, we talked about gravitational force, gravitational constant. These are all tiny little pieces of a very large topic. Electricity, the very large topic, of which we will study small little pieces of it. So some textbooks will, I think in one of the videos I talk about defining electricity, and I pulled up 4 different definitions that I found online, of which they are, you know, all related to electric charge and what it does, but I think only one of them I actually agreed with. But they were all subtly different. So for this course, electricity, huge topic, of which we will study charge, electric force, electric potential energy, and so on. Now, there is what I'm going to call the 99% rule when dealing with electric flow. Well, actually, before I do that, I'm going to break it like this whole first bit up into, not necessarily make that easy for you to see. Electrostatics. This is chapters 18 and 19 pretty much. That's test 1A. And electrodynamics, which is pretty much chapters 20 and 21, test 1B. Anyone want to tell me what the difference between these two are?
One's static, one's dynamic.
And what does that mean in physics?
One's still, one's moving.
There we go. Now, do charges actually stand still? We will pretend. There's going to be some subtle movement. Even in the best situation, there's going to be some subtle movement there. It will never be completely still. And then if you get into the quantum stuff, all the rules get thrown out the window, which we will touch on at the end of the course, maybe. All right, so in terms of electric flow, there's 2 rules that if you sort of take into heart, you're going to be correct about charge flow 99% of the time. In actually everyday life, of course, on a test. Who knows how I'm going to word that question? 99% rule. 99% of the time, if a charge moves, I'll use the word flow to indicate it's not just vibrating back and forth. If a charge flows, the charge is the electron. If I want to move protons, protons are at the core of the atom. If I want to move the protons in this paper, here I'm about to move the protons in the paper. There we go. If I want to move the electrons are on this outer shell, and I can just rub and scrape some electrons off. Electrons are easy to pull off. Really, if you're going to move a proton, and for what we have, you're moving the entire object, or at least parts of it. Questions up to here? Am I missing something? There we go. PVC. Rabbit fur. I do state this in one of the videos, but rest assured that the rabbits were moving down into the tropics. They did not need their fur because it's really hot, so they gave them the fur willingly for science, and the rabbits are now living happily in very temperate area of the world. I assume. All right, so what I'm doing right now is I'm rubbing the rabbit fur against the PVC. Electrons are being transferred from one to the other. Now, if you do this in summertime, this demonstration really, really sucks because humidity really destroys it. But if any of you have shocked yourself when you touch the car, you know that wintertime, really great for holding on to charges. Now, the electrons were transferred. So one question is, did the electrons get transferred onto here or onto here? Gut feeling. So we got 2 for gut feeling for this. Pardon? Got fur. Pipe. Is physics by democracy actually going to work? Well, not as much as it was. It's the pipe. Now, how do I know this? Well, because other people have told me. There's this thing called triboelectric effect, that when you rub 2 things together, one is more apt to give up electrons, the other one is more apt to take electrons. There is a list, if you typed in, in Google or whatever you use, hopefully not Microsoft Edge, because as we all know, Microsoft is evil. And although Google's getting to be that way too. What's next? Anyway, I digress. So there's this triboelectric effect, and there's just a list hierarchy, and towards one end, things are more apt to become positive when rubbed against something else, and at the bottom, things become more negative. Plastics tend to be at the bottom, more negative side. All right, so this is charged, I'm claiming, but how can we actually tell if it's charged or not? Okay. Well, we'll use our handy dandy spectroscope. It is an electroscope. And
Yeah, I can see.
there are 2 metal leaves in there. They are aluminum, I believe. Possibly gold foil, I don't think so. I'm not quite sure if there's a place where everyone can actually see it. So right now, the 2 leaves are kind of dangling down low. I'm going to bring this closer to it, and the question is, if it is charged, what is going to happen to the 2 leaves?
They'll start.
I'm not quite sure what the hand gesture was.
Never mind. Continue.
They're going to sparkle?
No, never mind. Just continue. I can't find my words. Go ahead. Go ahead.
Someone else want to fill in her words?
Might twitch a little.
They might twitch, okay. Do you want to speculate as to why, or you're just figuring something's going to happen?
Oh, I just figured something will happen.
Okay, Erica?
It's either going to repel, move away from it, or get closer to the object.
No.
No?
Possibly. Right now, this is neutral. All right, so let's find out. It twitch a little bit there.
Yeah. Whoa.
That is crazy.
All right, so a couple of different vocab words here. Now, if this had been summertime, it would not have done anything at all because that would have been neutralized. So eventually we need to get to the question of why does the summertime neutralize it faster? Go for it.
I have a thought. It's because there's more water in the air and the water molecule is already, no.
Oh, you were there.
Well, water molecule has a charge already on it because of the hydrogens and the oxygen. So my guess is that's why it changes it.
You are so very close.
Ugh.
What is it special? Because a water molecule is neutral. Like, what do you mean?
Wait, what did you say?
Water molecule is neutral.
Oh,
It's just as much positive as negative.
yeah.
So what's special about the water molecule that would cause it to actually take on extra charge?
It has space for taking on electrons, right?
Why?
It's moving slower.
Wait,
Pardon?
The movement is slow compared
Yep.
to when it's.
It's not a matter of that.
It's because
I missed what you said.
I was gonna say something about an electron shell, maybe. I don't know.
An electron what?
An electron shell. You know
You probably connected. That's, I think, the long way to go about it.
it is because of the intermolecular forces that are holding the hydrogen and oxygen together. Yes? No?
All right.
A type of intermolecular force.
Again, I think along with Luis's suggestion that we could connect it, but that's not necessarily the simplest way. What do you know about the oxygen molecule? Besides, sorry, not oxygen molecule, about the water molecule. What is it comprised of?
the 2 hydrogens and 1 oxygen.
Okay, so I got my oxygen right here. It's the big one. Where are the hydrogens?
They're attached like that, like Mickey gears.
Like that?
Sure.
Although I generally see it more like that.
Yeah.
I guess an upside down Mickey. Yeah. Now, a hydrogen atom, what's in a hydrogen atom? What does a hydrogen atom have to have? There we go. Yeah, it has a proton. So a typical hydrogen atom has a proton, and it's got one